In this video, we're going to look at how to decide which mechanism operates in a given reaction. That is, if you have a substrate that can do substitution or elimination, which of the mechanisms, SN1, SN2, E1, or E2, would the substrate undergo? Why would we need to bother knowing this information? First, we need to be able to predict products of reactions, given what comes before. If we have an alkyl halide or an alkyl with another leaving group on it, and we have it react with a nucleophile, it can give a substitution product, or if it's a beta hydrogen, we can give an elimination product to create an alkene. Also, the mechanism determines the stereochemical outcome of some of these reactions. In particular, if it's an SN2 mechanism, we're going to get inversion during substitution, racemization if the mechanism is SN1, and if we're doing an elimination reaction through an E2 mechanism, we're going to get only the products possible from anti-periplanar elimination from opposite sides. We might also be desiring to make a certain product through synthesis. In order to do that, we need to know how and what conditions are necessary to give that product, and the product outcome would be determined by which mechanism occurs. So when we start off to figure out which mechanism to use, we have to identify the reactive site on the molecule. Where is the leaving group? For example, is the leaving group on a carbon that is primary, secondary, tertiary? Is there an allylic or benzylic site nearby? If the leaving group is on a single carbon atom, methyl, then SN2 is the only possibility of these four reactions. If there's a beta hydrogen, like there's shown in the picture here, where we have a leaving group beta hydrogen, if not, then you cannot do elimination. And if an allylic or benzylic system is present, it would give especially stable SN1 and E1 reactions. And by allylic and benzylic, I mean the position of the leaving group is next to a pi bond. Position of the leaving group is next to a pi bond here as part of the benzene ring. The way in which one mechanism occurs rather than another is it's all about the relative rates. Theoretically, any of the mechanisms could happen. However, under a given set of conditions, one or two of the mechanisms is going to happen more rapidly than the others and determine the outcome. The mechanism is determined in part by how hindered the substrate is, how stable a potential carbocation that would be formed is, how nucleophilic the nucleophile or base in the reaction is, how basic the nucleophile or base in reaction is, the solvent, whether it's polar and whether it's protic or aprotic, and the temperature of the reactions. These are all things that we can modify and change the mechanism. Now here's a chart I prepared many years ago for classes that summarizes all the things that affect the rates of SN1, SN2, E1, and E2 reactions. In particular, the bimolecular reactions, SN2 and E2, the rate is actually determined both by the concentration of the alkyl halide and the concentration of the nucleophile or the base, so that adding more of them, more concentration of either of these, would increase the rate. The unimolecular reactions, SN1 and E1, depend only on, the rate only depends on the concentration of the substrate. And as you look up here, the nucleophile or base strength doesn't affect the rate of an SN1 or E1 reaction. However, it can affect the rate of competing reactions such as E2. The leaving group is the same for all of them. The weaker the base, the better the leaving group. The alkyl group is of prime importance in determining how fast a given reaction goes. In particular, SN2 goes faster with less hindered substrates. So starting with methyl, which go fastest, all the way to tertiary, which are the most slow. They are too bulky to ever undergo SN2. On the other hand, SN1 and E1 also is completely determined by how stable the carbocation formed is, so that tertiary is faster than secondaries, very much faster than primary or methyl, which will never undergo one of these unimolecular reactions unless no, unless it is benzylic or allylic. E2 reactions also are somewhat favored by tertiary, secondary, primary, but the effect on rates is much smaller than for SN2 or SN1 or E1. Another variable is your solvent. SN2 reactions in particular prefer aprotic solvents, ones without OHs and NHs. SN1 and E1 reactions prefer very high dielectric or polar solvents. The more polar the solvent is, the faster the reaction. And finally, temperature is one of the things we can control, and lower temperatures tend to favor substitutions, SN2 or SN1, compared to eliminations, which tend to be favored by higher temperatures. So there are several ways to use this information about rates to determine which mechanism takes place for a given substrate. One of them is outlined in a series of flowcharts at the end of 14C in your Stromanis workbook. So here are examples on how to use the Stromanis flowcharts. First, you look at the substrate and you decide what it is. This one happens to be primary, and it's not allylic or benzylic. So with primary, the most important things to notice are that the substrate's not very hindered, so that SN2 is possible, and that if the bromine were to leave, it would leave a primary carbocation, very unstable. So, if you have a primary leaving group, your only possibilities are SN2 and E2. You're not going to get SN1, E1, which require a free carbocation to be formed. In this particular reaction, you can ask yourself, is the OH, because you know that this is Na plus OH minus, is the OH a good nucleophile? It's small, it's negatively charged, it's not delocalized, that makes a good nucleophile. So we would follow the chart down the pipe that says good nucleophile. Second question to ask is if OH a strong or a weak base. OH minus is a relatively strong base. So we follow the chart down to the strong base branch. And our next question is temperature. Is this particular reaction indicated to be hot? Generally, if it's indicated to be hot, something will be given over the arrow, like a temperature 100 degrees C, or heat, or a delta, Greek delta sign. None of those things are here in this reaction, so it's considered to be cool, a room temperature reaction. And that would indicate SN2 mechanism predominating. In general, SN2 is the preferred pathway for primary. Sometimes E2 can happen, but generally only at higher temperatures with very bulky bases that are hard to add as nucleophiles. That would send us down this path. And E2 can be helped a little bit by the fact that protic solvents slow down SN2, allowing E2 to catch up. So if this reaction had been run in heat and a protic solvent, E2 would take over. If we have a secondary or a primary allylic or benzylic substrate, and the leaving group is attached to that secondary carbon here, we then follow the secondary leaving group chart. First question again to ask is if our nucleophile base, which is this Na plus O minus, OH minus, if it is a poor or weak nucleophile. Because the OH minus is charged and small, that would make it a good nucleophile. We then ask ourselves if the OH minus is a strong or weak base. In this case, it is in fact a strong base. Then we ask ourselves, are we at room temperature or are we heated? Here's our heat over the arrow, so we're hot. And that's going to tend to prefer E2. Generally, anytime there's a strong base, you have to consider E2 as an important contributor unless it's primary. And even then, if it's bulky, okay, unless it's primary. Okay. To speed the E2 up even more, or to slow down the competing SN2, we could use a protic solvent here, such as water. What if we have a secondary substrate that also happens to be allylic or benzylic? Now we have a substrate that not only could form a secondary carbocation, but that carbocation would be resonance stabilized. Again, our question is this a good or poor nucleophile? It's still relatively small. It does have a lone pair for nucleophilic addition, but it doesn't have a charge, so it would tend to be a fairly poor nucleophile. Our next question to ask, is there a strong base? Well, of course, water is not a strong base, so we go down the weak base pathway. Finally, we ask ourselves, what's the temperature of this reaction? There's no heat written over the arrow. We know we're going to get a mixture of E1 and SN1 because E1 and SN1 always compete, but at lower temperatures, SN1 is the major pathway. Finally, we have an example with a carbon attached to 3 different groups, tertiary, and we can do the same process for the given example. First, do we have a relatively good or relatively poor nucleophile? Well, this one does have an O with a minus charge, but it's not very small. So we're going to call it a poor nucleophile, but on this one it really wouldn't matter which pathway we get because the next question is going to be, is it a strong base? Most definitely O with a negative charge is a strong base. And so we're going to point down to E2, temperature doesn't matter at all. Solvent doesn't matter. In fact, when you have a tertiary and a strong base, no matter how good or poor the nucleophile is for that strong base, you're going to end up at the E2 position. And sometimes after working problems, students see that tertiary is always SN1 or E1. That's not true. If you have a strong base in tertiary, you do E2. The only rule for sure is that tertiary is too hindered to do SN2.